Okay, before we move on to tonight's homework, I did want you to look at one more thing, and that is to find a shortcut to that indicial equation, because based on some of the models of these differential equations you're going to solve with the Frobenius method, it can be very tedious to actually take the first two derivatives of the model and sub them into the original equation. So I want to show you a shortcut, a way that you can arrive there a whole lot faster. So let's look at the equation I just solved. X squared y double prime minus 4x y prime plus 6y equals 0. Now, in order to get to the indicial equation, we had to substitute in y equals the summation n equals 0 to infinity of a n x to the n plus r and its two derivatives. And then substitute it in and gather everything, and then once we reached a point where everything was under the same index and under the same power, we could pull out the indicial equation at n0, solve it, and then get our cases for r. See whether r was a double root, or see whether r differed by an integer or it differed by a non-integer. And those are basically the three cases. Well, let me show you a shortcut, a way to get there a little bit quicker. Okay? That way you won't have to really take this and its derivatives multiple times. What I want to do is show you a model of what all of these equations should look like. And they should look like this: x squared y double prime minus x p of x plus q of x y. Oh, x p of x y prime plus q of x y equals 0. What I want you to do is take every equation and put it into this form. This equation is already in this form, but many will not have a leading x squared. They'll have some other function there, in which case you want to divide through by it. Some of them won't have any coefficient, in which case you're going to want to multiply by x squared. Some will just have a coefficient of x, in which case you'll have to multiply through by x, because it must be in this form: x squared y double prime minus, and then whatever's sitting here, whatever function this is, it's always x times px. So factor an x out, and what remains is px, and whatever is sitting in front of the y is a qx. Many of these will be rational functions with numerators and denominators in x. Okay, once you have it in this form, basically, when you run through that process of taking the series definition of the Frobenius method, substituting it and its derivatives in here, you'll always end up with the following as your indicial equation. Always. It will always be r times r minus 1 plus px naught times r plus q x naught equals 0. And generally our x naughts are going to be 0. On some equations they won't be, because we won't actually be resolving it at x equals 0. We'll be resolving it at some other location. If you've got a leading set of parentheses that say has an x minus 3 squared, then we're going to be evaluating it at 3, in which case x naught you would plug in as 3. But most of the time x naught's going to be 0, which means you're going to evaluate q where x is 0, and you're going to evaluate p where x is 0, and that's going to sit here. These are both going to be constants because they won't be functions of x anymore. And that's what will make this a quadratic. And then when you solve that quadratic, you're going to end up with either two solutions that differ by an integer, you're going to end up with two solutions that don't differ by an integer, or you're going to end up with a double root. Those are the three cases that we're going to be working on. Let me show you this with one other Frobenius equation. So the one we're going to look at is 5x squared y double prime plus x plus 1 y prime minus y equals 0. Well, you can see it doesn't start with x squared, it starts with x squared over 5. So I'm going to divide through by 5. So that's going to make it x squared y double prime plus x times x plus 1 over 5 y prime minus 1 over 5 y equals 0. That's going to make qx equal to negative 1/5. It's going to make px equal to x plus 1 over 5. And that means p at 0 is going to be 1/5. And q at 0 is going to be negative 1/5. So that means the indicial equation, if I were to plug in the Frobenius solution and its subsequent derivatives, collect like terms, do everything necessary, this is what I'll end up with. I'll end up with r times r minus 1 plus 1/5 of r minus 1/5 is equal to 0 will be the indicial equation. So I can immediately now expand this and solve for the values of r, and that would tell me the nature of the solutions to this equation. And then I could start guessing, hey, if r is equal to this solution and this one, and I could start looking at the expanded series and make predictions on what the solutions will be. We'll work more on those tomorrow. Tomorrow's lesson is really going to be about differentiating the three cases and how it is you handle it if the roots differ by an integer, if they differ by a non-integer, or if they are double roots. For today, I just really want you to get comfortable taking these equations and finding the indicial equation, and then from there, looking at the nature of the roots.